Hello dear students, this is our lecture for probability theory course. As we mentioned before that the discrete random variables can take only a countable number of possible values. On the other hand, a continuous random variable x has a range in the form of an interval or a union of non-overlapping intervals on the real line. Also, for any x element in real numbers, probability of x equals 0. Thus, we need to develop new tools to deal with continuous random variables. The good news is that the theory of continuous random variables is completely analogous to the theory of the discrete random variables. Indeed, if we want to oversimplify things, we might say the following. Take any formula about discrete random variables and then replace sums with integrations or integrals, and replace BMF or probability function with probability density functions, BDFs, and you will get the corresponding formula for continuous random variables. Of course, there is a little bit more to the story, and that's why we need a chapter to discuss it. In this chapter, we will also introduce mixed random variables that are mixture of discrete and continuous random variables. We have in fact already seen examples of continuous random variables before. Let us look at the same examples with just little bit different wording. If you choose a real number uniformly at random in the interval a and b and call it x. By uniformly at random, we mean all intervals in A and B that have the same length must have the same probability. Find the CDF of x. As we mentioned, this is almost exactly the same problem as a previous example, with the difference being in that problem we considered the interval from 1 to 2. In that example, we saw that all individual points have probability. For example, probability of x equals 0 for all x. Also, the uniformity implies that the probability of an interval of length L in A and B must be proportional to its length. So, the probability of x element in the interval x1 and x2, where a is less than or equal x1 is less than or equal x2 is less than or equal b. We can conclude that the probability of x, which is element in the interval of x1 and x2, is equal to x2 minus x1 over b minus a, where a is less than or equal x1, less than or equal x2, less than or equal b. Now let us find the CDF by definition of the function of CDF, which is f of x equal probability of x less than or equal x. Thus, we immediately have f of x equals 0 for x is less than a, f of x equal 1 for x is greater than or equal b, and x is between or equal a and b. We have f of x equal probability of x is less than or equal x, and it is equal to probability of x is element in the interval of a and x, which is equal to x minus a over b minus a. Thus, to summarize, f of x equal 0 for x is less than a, x minus a over b minus a for x is between or equal a and b. 1 for x is greater than b. Note that here it doesn't matter if we use less than or equal, as each individual point has probability 0, as we know before. So for example, probability of x less than 2 is equal to probability of x less than or equal to. And figure 4.1 shows the CDF of x, as we expect the CDF starts at 0 and ends at 1. It is continuous from right function. On big difference that we notice here as opposite to discrete random variables is that the CDF is a continuous function. It doesn't have any jumps. It is a continuous. Remember that jumps in the CDF correspond to points x for which probability of x equal x is greater than 0. Thus, the fact that the CDF doesn't have jumps is consistent with the fact that probability of x equal 0 for all x. Indeed, we have the following definition for continuous random variables. A random variable x with CDF f of x for x is said to be continuous if f of x is a continuous function for all x elements in real numbers. We will also assume that the CDF of a continuous random variable is differentiable almost everywhere in real numbers. The probability density function for continuous random variables. To determine the distribution of a discrete random variable, we can either provide its probability function or cumulative distribution function. For a continuous random variable, the cumulative distribution function is well defined, so we can provide the CDF. However, the probability function doesn't work for continuous random variables, because for a continuous random variable, probability of x equal 0 for all x element in real numbers. Instead, we can usually define the probability density function, BDF. The BDF is the density of probability rather than the probability mass. The concept is very similar to mass density in physics. Its unit is probability per unit length. To get a feeling for BDF, consider a continuous random variable x and define the function of f of x as follows. The function f of x for x gives us the probability density at point x. It is the limit of the probability of the interval x and x plus triangle divided by the length of the interval as the length of the interval goes to 0. Remember that probability of x is between x and x plus triangle equal to f of x for x plus triangle minus f of x. So we conclude that f of x for x is equal to limit from x for f of x plus triangle minus f of x over the triangle, and it is equal to f of x is differentiable at x. Thus we have the following definition for the BDF of continuous random variables. Consider a continuous random variable x with an absolutely continuous CDF f of x. The function f of x defined by f of x equal d of f of x over dx equal the differentiable for f of x is called the probability density function of x. Let us find the PDF of the uniform random variable x discussed in example 4.1. This random variable is said to have uniform A and B distribution. The CDF of x is given in the equation 4.1 by taking the derivative for the function. We obtain the function of x will be 1 over b minus a for x is between a and b, and 0 otherwise. Note that the CDF is not differentiable at points a and b. Nevertheless, as we will discuss later on, this is not important. Figure 4.2 shows the PDF of x. As we see, the value of the PDF is constant in the interval from a to b. That is why we say x is uniformly distributed over a and b, or over the interval of a and b. The uniform distribution is the simplest continuous random variable you can imagine. For other types of continuous random variables, the PDF is non-uniform. Note that for small values of sigma, we can write probability of x is between x and x plus sigma may be equal to f of x times sigma. Thus, if x for x1 is greater than f of x for x2, we can say that the probability of x is less than x1 and greater than x1 plus sigma is greater than the probability of x between x2 and x2 plus sigma. The value of x is more likely to be around x1 than x2. This is another way of interpreting the PDF. Since the PDF is derivative of the CDF can be obtained from PDF by integration. F of x is equal to the integration from minus infinity to x for the function of x for u du. Also, we have the probability of x between a and b equal f of x for b minus f of x of a, which is equal to integration from a to b for f of x to u du. In particular, if we integrate over the entire real line, we must get 1. That is, the area under the PDF curve must be equal to 1. We can see that this holds for the uniform distribution, since the area under the curve in figure 4.2 is 1. Note that f of x for x is density of probability, so it must be larger than or equal to 0, but it can be larger than 1. Let us summarize the properties of the PDF. Consider a continuous random variable x with PDF f of x for x. We have, first, f of x for x is greater than or equal 0 for all x are element in real numbers. Number 2, integration from minus infinity to plus infinity for the function of f of x for u du equal 1. Number 3, the probability for x is between a and b equal to f of x for b minus f of x for a, which is equal to integration from a to b for f of x for u du. Number 4, more generally, for a set A, probability of x element in A equal to integration for A for f of x for u du. In the last item above, the set A must satisfy some mild conditions which are almost always satisfied in practice. An example of set A could be a union of some disjoint intervals. For example, if you want to find B for x element in the interval of 0 and 1 union the interval of 3 and 4, you can write probability of x element in interval of 0 and 1 union interval of 3 and 4, which is equal to integration from 0 and 1 for the function f of x for u du plus integration from 3 to 4 for the function of f of x u du. Let us look at an example to practice the above concepts. Let x be a continuous random variable with the following PDF: f of x equal to c times e with power minus x, and the x is greater than or equal 0 and 0 otherwise. Where c is a positive constant, find c, find the CDF of x, find the probability of x between 1 and 3. Number A, to find the constant c, we can use property number 2 above, in particular that the integration from minus infinity to plus infinity is equal to 1, and by applying this property we have integration from 0 to infinity c e with power minus u du equal to constant c times minus e with power minus x from 0 to infinity, which is equal to c, and then we must have c equal 1. Number B, to find the CDF of x, we use f of x equal integration from minus infinity to x for f of x for u du, and then we obtain the CDF, which is equal to integration from 0 to x for e with power minus u du, which is equal to 1 minus e with power minus x. Number C, we can find probability of x from 1 to 3 using either the CDF or PDF. If we use the CDF, we have probability of x between 1 and 3, which is equal to f of x for 3 minus f of x for 1, and by applying that formula we obtain e with power minus 1 minus e with power minus 3. And thank you.